how to use scope graphs as types.
Yes. Is the audio okay like this? All right. Thank you for coming. So, my name is Hendrik, and I'm here to tell you about the work that we did with Casper Bach-Paulsen, Arjen Rauwvoet, and Ilko Visser on how to write declarative and executable type system specifications. And I want to start by diving a little bit into the problem of achieving this goal. So very often we are in this situation where we have a set of declarative typing rules that say what is a well-typed program, and then we have some kind of algorithm that we use to actually type check our programs. We need to develop both. We want to keep them aligned. We want to, we hope that they express the same thing, right? And this takes effort, and this is sometimes actually very hard to prove. So instead of having these different artifacts, it would be much nicer to have one specification, one declarative specification that is also executable as a type checker. So this is the goal of our work. But it turns out that this goal is sort of hard to achieve because of the different name bindings patterns that we can find in different languages. So what we would like to have to write these declarative executable specifications is a uniform representation for binding, for name binding, and we want to abstract over the particular issues of execution order that we need to address when we write type checkers. I want to go through a few textbook examples, as they were called before, to see what kind of binding representations that we find there and how they work with regard to these two issues. So the first thing is lexical binding. This is a very common binding pattern. We find it, I think, in almost all languages. So in this example program, we have a let that binds an x of type int. And then in the body, we have another let which binds a function. The function binds a parameter x. And finally, we apply the function to x. So if we look at the name resolution for this example, we see that this x refers to the one from the outer binder. But there's also an x reference in the body of the function. And, well, we have two options here, right? And, of course, we expect it to resolve to the binder of the function. That means that there's some kind of shadowing going on with respect to the other binder. And if we think about a representation that this type of binding has, usually in type system specifications in some kind of typing environment, it's an ordered list of names and types pairs. And if we think about a type checker that would use this representation, then it needs to construct this environment in a kind of top-down manner, because these identifiers are visible usually in the subtrees of the binding constructs. So you have some kind of top-down construction if you want to execute something like this. Now, of course, we don't only have this kind of lexical binding patterns. We also very often have binding that's related to our types. So I have an example here of record types. And what we see here is that, well, we have this record. It's some kind of unordered representation that we want to represent these things with. So the order of the fields doesn't matter. And if we think about how to resolve these things, well, the p, of course, is just a lexical variable like the one in the previous example. But if we want to resolve y, we want to actually do this in the scope of the type, because the binder is part of the type here. And if we think about a type checker that does this kind of thing, well, we need to realize that there's now some kind of interleaving that we need to support, because we cannot resolve all the names anymore before we know any of the types. And finally, we usually want to organize our programs into bigger chunks. Oh, wait, before that. So there's a general point here that there's all kind of different types with different scoping and binding structure, which basically describes the underlying data that the type represents. And these representations are also very often language specific. So for example, class types are usually designed specifically for the particular language that you are writing the type system for. Now finally, we want to organize our programs, so we have some idea of modules or classes or something like that. So here we have an example with modules. So we have a module A, and it imports the module B, and then both modules contain a definition. Now the B, of course, refers to the other module, and because of the import statement means that this reference Q over here can be resolved to the definition in the other module. And these kind of bindings patterns, they require some kind of global module table where we describe the interfaces of the modules that we are dealing with. The representations of these interfaces are very often language specific. And if we think about a type checker that type checks something like this, then we have some kind of staged approach where we first compute this module table and we find all these interfaces, and then based on that we check the bodies of the modules. So what have we seen so far with respect to these two topics when it comes to common binding representations? Well, there are many different representations, and they are completely or partially language specific, and they're ad hoc, so it's hard to reuse them between different language specifications, for example. And if we look at these execution order concerns, then we see that if we want to execute something as a type checker, well, we need to be concerned with interleaving, with staging, and all these things, once they show up in our typing rules, they make the rules less declarative. So we don't want that, because we wanted to have declarative specifications that we could also execute. So what is our approach here? Well, for this uniform binding representation, we will be using scope graphs. And scope graphs are a language-independent, a uniform representation for binding, and they also give a way to do name resolution in this representation. And we use a constraint language, Statix, where you can write declarative type system rules, which are based on this name-binding representation of scope graphs. So I will talk about these two things, and I will start with explaining what are scope graphs, and after that I will show how they are used and show up in Statix type system specifications. So here we have our lexical binding example again. It's exactly the same program. And on the right there, we see the scope graph that represents the binding in this program. So these scope graphs, they consist of scopes, of declarations, and they are connected with labeled edges. And in this case, the P label is used to indicate that we're talking here about lexical parents. So scope 2 is a subscope of scope 1, and scope 3 is a subscope of scope 2 in this case. Now, if you want to resolve a name, then it amounts to doing a query in this graph to the declaration that we are interested in. So let's say that we are interested in the resolution of this x in the function body. Now, the query consists of, it takes two parameters basically that control how we can do resolution here. So we are going to query in the scope, in scope 3, which is the scope of the function. And the first ingredient of these queries tell us, well, what do we want to resolve to? And in this case, of course, we want to be able to resolve two things in the lexical context. So we can describe that using a regular expression, which tells us that we can step to any scope that is reachable with these P edges that basically tell us where the lexical context of this particular scope is. But of course, now we have two possible paths in the graph, right? Because we can go to the X in scope 1, which is the one from the let here, and we then go to the one in scope 3, which is the parameter that is bound by the function. So we have a second ingredient here, which is an ordering that tells us, well, which one do we consider to be more specific? And in this case, we say, well, we prefer local declarations over declarations that are reachable sort of in the context by taking any p steps. And this results in a resolution to the x in scope 3 in this case, but not to the one that comes from the outer let. So how do we fare if we start to look at these scoping structures that are related to types? So here's a record example again. And we see that in the scope graph, we can very naturally model these record types. We just create a scope, and in this scope, there are the fields with their corresponding types. And well, there's obviously a correspondence between our intuition of records and this representation in scope graphs. And of course, the type of the literal has a similar structure. And then, well, our insight was what you can do here is simply use the scope as a representation of the type. So what we say is, well, the type of P in this case is the record that is represented by scope 2. And by using scopes as types in this way, we get a very uniform approach to dealing with type-dependent forms of name resolution. And basically all of the power that scope graphs have are now also available for the kind of binding that you have in your types. And if we look at, so if we now start doing resolution, then of course we resolve P, which gives us the declaration in scope 1, and then we know the record scope, and now resolving Y amounts to doing a query in the record scope that we got from the type. Now if we look at our modules, first of all we see a similar encoding, so we have a global scope, scope 0 in this case, which correspond to your intuition of the global nature of the module table, right? And this scope contains the declarations for the different modules, and they're also typed by the scope that represents this module. And now we have this import statement over here. Well, it refers to some B, so this B is queried in the graph, and it will tell us that module B is typed by scope 2, so scope 2 is the representation of the module in this case. And the actual import mechanism is represented by this edge over here between the two scopes. And now what we see is that if we want to resolve this reference, well, obviously we can follow this import edge that we created in the graph, which allows us to resolve to the declarations in the other module. And of course, this kind of priority mechanism can be used to say whether we want to prefer local declarations over imported ones, or maybe the other way around. So here you have flexibility in the design that you want for your language, basically. So what have we seen so far? Well, we have scope graphs, and they are a language-independent model for name binding. They capture different kinds of binding that commonly occur in languages, and we can resolve names in this representation by doing these graph queries, and we can use the parameters to basically get the resolution behavior that we want. So now I want to talk about Statix and how we can use this model to write, first of all, how can we write declarative rules? And second of all, how can we execute those? So I will start by showing what these rules look like. I will use the module example here. I realize that the rules are a bit low here, so I hope you will be able to follow what's going on. So first of all, if we look at the rules over here, they are syntax-directed rules that talk about what kind of graph corresponds to a certain program. So it makes assertions about the shape of a graph that we want to have for a certain program. And we can use these kind of queries to do name resolution where this is appropriate in the rules. So these kind of rules, they basically say, well, a well-typed program is a program which has a scope graph which corresponds to whatever assertions that we make in the rule, and for which other constraints like query constraints, type equality constraints, stuff like that are satisfied. So let's spell this out a little bit more in detail. So if we look at module B, then we have the rule for modules over there. And basically this bit here states that there is a scope, which is called SM in this rule, which is particular to this module. So this upside down triangle here indicates that the module in a sense is the owner of the scope, so it cannot be the same scope in the model as the scopes that belong to other modules. There's a declaration in the global scope for this module, which is typed by the module scope, And of course, the module scope itself is a subscope of the global scope, so there's this edge with the P label again. And then, of course, the premise after that basically says that whatever are the statements in the module, they should always be, they should also be well formed. So what you see here is that this rule doesn't make any distinction between the parts that are traditionally part of the module table. So the declarations and the definitions are in there. But everything sort of that belongs to this language construct is just written in this single rule. If we look at the import rule, then we see here that there's a query, and this query tells us basically where the which module that we are importing. And this query is, of course, typed with a module scope, and then we say that for this statement to be well typed, or well formed in this case, there has to be an edge in the graph with this I label. So these are the kind of rules that specify the scope graphs that we want for the programs that we want. And apart from that, well, there are sort of type constraints that are not in this example. But of course, they are also part of the same rules. So now if we start thinking about how can we execute these kind of rules, then what we need to realize is that, of course, we don't have the graph beforehand. So we have a program, and then during our type checking process, via some mechanism that we will come back to later, we are constructing this graph. And then at some point, of course, there is this import edge that needs to be created because it was part of the graph, right? However, to do that, we do need to resolve this modular reference in the same graph that we are constructing at the moment. Because this reference tells us basically where that the edge, the import edge, should go. So there's a dependency here, which means that in our execution mechanism, we need to make sure that we can interleave querying the graph and constructing it. So we want to do these queries in an incomplete graph. And the question is, well, can we do this? Sort of, is this sound? And then we say, well, if we can do the query in such a way that the result will also hold in the final graph, then we're okay with doing that. However, if this is not the case, then we don't want to do that. And an example of why this is important is if we would have this graph somewhere during our type checking process, and we would try to resolve Q here. Now, the import edge here is missing, so of course, Q doesn't resolve in this particular graph. Now, instead of generating an error here, because we happen to try to resolve Q earlier, we use a mechanism to approximate the possible extensions that the graph can still have during the rest of the type checking process. And instead of saying that Q does not resolve, we actually delay the resolution of Q. And we try again later, basically, when we know more about the graph. So, based on this idea, we have an execution mechanism which basically executes our specifications by treating the typing problem as a constraint problem. And we do rewriting of the constraints based on the rules that are in our specification. This is a committed choice algorithm, so it doesn't do any backtracking. And it uses this safety mechanism to ensure that the order in which we solve the constraints, which is non-deterministic in general, but we do enforce some order to make sure that we don't resolve any queries too early, basically. So we start with an initial state here, and then, well, we rewrite some stuff, and we start constructing the graph. And of course, we hope that we can reach a final state where we have no constraints left, and then we know that the scope graph that we created is basically the scope graph corresponding to this program, and that all our type constraints worked out, and everything is well. How much time do I have? Two minutes? All right, so that should work out then. So can we always, does this always work, this mechanism? Well, there are some obvious cases. They're not always obvious maybe when you write them, but sort of if I represent them like this, I hope they're obvious to you. Where you can write rules that basically introduce a kind of cyclic dependency. So you are querying something in a certain scope, and basically, well, for the query to succeed, you need to construct a certain edge, but the construction of this edge depends on the query. Well, obviously, these kind of situations we do not solve. So here, a constraint solver would get stuck, and you would basically get an error that not all the constraints could be resolved. Obviously, you want to avoid writing these kind of cyclic dependency patterns in your specification. So we had scope graphs. I told you about scope graphs as a language-independent representation of name binding. And now I've shown you Statix, where you can write these declarative rules based on this model to specify your type checker. And we have this execution mechanism to actually execute those specifications for your programs by using a constraint solver approach. We implemented all this, so here's a bit of solver code. Don't read this, please. But basically, there's a program and a static specifications that go into this solver, and then out, hopefully, come a type program and a scope graph that corresponds to the program. Or, of course, if we are not able to solve all the constraints or there are conflicts, then you would get error messages or something like that. And for the evaluation of our approach, we have implemented a few case studies. So for each of these case studies, we wrote a specification in Statix. We wrote a whole bunch of tests to test the typing and the name binding behavior of this particular language. So we wrote positive cases where we say, well, this program should type check and, I don't know, identifiers should get certain types, names should resolve to some places. And we wrote a whole bunch of negative tests that said, well, this program shouldn't type check. And then we ran all of them, and they all became green, so we were very happy about that. It did take some debugging of the specs, obviously. We did this for 3 languages, which had different language features that we can find in the wild, let's say. So we did it for the simply typed lambda calculus with structural records, where we have structural types and we have structural subtyping. So we have these kind of typing relations that we needed to express there. We did it for system F, which has parametric polymorphism. And finally, the biggest case study that we did was Featherweight Generic Java, which has nominal typing, class extension, and based on that also nominal subtyping, but also generic, so it brings a few of these ideas together. So with that, I conclude that I showed you a way to write declarative executable type system specifications. And we want to do that so that we have one canonical specification, but that we can still have a type checker based on that for free. And I showed you Statix, where you can write these typing rules based on a model for name binding, which are scope graphs. We have an execution mechanism for this for these specifications, and we validated our approach by implementing a few case studies, which told us that we were able to express the language features that we had there, and that the solver was powerful enough to actually resolve all of the cases that we gave it. Thank you.
Do we have any audience questions?
Thank you. So for subtyping, do you have a special kind of edge in your scope graph to resolve, or I think it will be for inheritance?
Yes. So that is indeed for Featherweight Java, for example. You have a similar edge as the import edges for modules, for example.
And then to resolve subtyping, do you have these specification rules, or you have some special kind of queries?
So we use special kind of queries, but basically the structure of the graph also tells us the inheritance structure, right? The class extension structure. So basically we express subtyping between different class types as a particular kind of query over the graph, where we see if there is a path via these extension edges to the supertype that we are trying to find. Basically.
Okay, cool, thanks.
So what do you do when there are more possibilities in actually resolving a variable? For instance, what happens with inheritance? Say you have like a class A, which has a field X, and a class B, which has a field X, and then you have a class C, which inherits from A and B, and now there's like this ambiguous meaning of X. So have you thought about this, or what happens there, or can you specify, I want to disallow this, or maybe I want to prefer this over the other?
So if I understand your question correctly, you mean if you have ambiguous resolution, so you have multiple X's that you can reach?
Exactly.
How do you deal with that? Yeah, so we are not very opinionated about that because there are languages where you have situations that there are multiple definitions, and I know maybe you just want to check that they all have the same type, but you don't care how many there are. So actually, when you do these kind of queries, you get a bunch of results. And then it's basically up to the specification writer whether they want to say, well, it really should have been one, or that you want to compare these results in a certain way, or that you don't care how many you get. So this is up to the person writing the specification, basically.
Okay, thank you.
Take one more question, and then we'll let you get to lunch.
Thank you. So I would like to view your framework as a tool to compare the complexities of languages in terms of like how their scopes are related to each other. So from your case studies, can you say that, for example, STLC is simpler, for example, doesn't need cycles in its scope graph than, say, the system with inheritance?
So your question is sort of, is the structure of the graph simpler for for simpler languages?
Yeah.
Yes, indeed. So if you have STLC, for example, well, the structure is tree-like, which you would expect because also in your derivation, your typing context is also built in a tree-like way, right? But if you have modules, you might have modules that import each other mutually, for example. So then indeed you could get cycles in the graph and these kind of things.
Thank you.
Yeah.
Let's thank Kendrick and all of our speakers again.